Hello to all of our attendees. My name is Gabriela Andrade, and I am a marketing specialist here at GERS USA. I am pleased to welcome you to our webinar on protection schemes in power systems and smart grids that will be presented by engineer Leiniker Palacios, who is the product manager of our company. We thank all the attendees for their interest in our webinar and invite you to please leave us any questions you may have in the Q&A section visible on your screen. We also encourage anyone who's interested in further information regarding today's topic to contact us by email at info.neplan.ch so the proper team can contact you. To give a brief introduction of our company, GERS is an electrical engineering consulting group founded in 1981. We have more than 40 years of experience providing electrical engineering consulting services and have carried out projects in more than 45 countries. Our services portfolio includes overhead line designs, substation designs, testing, maintenance, power system studies, and product representation such as NEPLAN. NEPLAN is a power system analysis software widely used in more than 110 countries with more than 500 active customers. This software offers various functionalities and packages for the analysis of transmission, distribution, and generation networks, and also for the oil and gas sector and industrials. NEPLAN also covers various functionalities in the analysis of water and gas and heating networks. This makes this tool a comprehensive platform for the analysis of different energy systems. The content of this presentation is divided into 6 main sections, where Engineer Leiniker will begin with a brief introduction on the evolution of protection systems and electrical networks, and some concepts in power systems and smart grids. Next, he will cover different concepts regarding protection coordination schemes and some criteria commonly used in the analysis of these systems. Given the evolution of new technologies that have been incorporated into modern-day electrical networks, an overview of these protection schemes will be discussed to later present some simulation cases on the NEPLAN simulation platform. So I'm happy to introduce Leiniker Palacios to present the technical aspects of this webinar. Welcome, Leiniker.
All right. Thank you very much, Gabriela, for your introduction. Good morning for all the attendees in the US and Americas, afternoon in Central European time. It is my pleasure to present this webinar about protection schemes in power systems and smart grids. As Gabriela said, we are going to present this webinar in 6 main topics that are presented in this slide. For doing that, I will start here with a brief introduction about the evolution of the protection schemes in the electrical networks. In that case, I am showing here some pictures from our museum that we have in one of our offices in GERS. We have in our office a real synchronous generator, and that generator has on the background this protection system that is mainly composed by all devices that works with electromagnetic field. The theory means that according to the signal that we have in the mobile contact, we will be able to connect or disconnect the 3-pin signal in order to protect the machine. These kind of protections were highly used in the years of 1970, but after 1980, we are having an evolution of new technologies that today are part of the intelligent electronic devices, also known as IEDs, since the numerical relays have allowed to be used in different technologies for the implementation of different strategies on modern electrical networks. Some of them are based in communications, some of them are based in protection logics, control logics, and the possibilities for the implementation of smart grids. Today, we know that we have different generation resources that are based in the new technologies. Conventional machines and inverter-based resources are highly used in the new generation of the systems that I will represent here in this slide. We have here how the conventional distribution system use conventional elements on the network. But we can see that today we are opening a new generation of small power system, also known as microgrid, what once we are able to integrate digital technologies and we are able to automate the system for specific target functions, we are opening the smart grids concept. However, the smart grids concept is not only for the distribution network. The smart grid concept covers many features in the different type of systems that we have in the electrical networks. For example, I am showing here in this slide some characteristics and some benefits about the smart grids. Typically, they are self-supported. They don't have a specific size. They promote the use of renewable sources, but we know that they are not mandatory in some aspect. However, when we speak about the environment impact, renewable sources are eventually promoted in order to improve this kind of impact. The smart grid use communications and modern technologies like the intelligent electronic devices that I presented before, like the advanced metering infrastructure, like the energy management systems, distribution management systems, the PMUs, among other technologies that we are able to use currently to solve many engineering challenges that we are having today. I will show them some of them in this presentation, but also I will present here some benefits about the smart grids integration. For example, the network restoration schemes, the generation optimization, reliability, resiliency, efficiency and cost reduction, environment impact, and demand response. Well, speaking about some general concepts about the protection schemes in power system, let me answer first the question, why protections? And if we know that in the power systems we have many events that can be caused by different reasons. For example, lightning, the aging of insulation, the equipment failure, animal presence, the rough environmental conditions, branch fault, improper designs, maintenance, or operations. They are some events that they can occur in the network. However, if we implement proper protection schemes, we can see this kind of message that they are essential to detect fault conditions, clear them, and restore the healthy portion of the system. However, they have some requirements. Some requirements in order to improve the reliability of the system that has two components, dependability and security. Because we have to ensure that the protections work properly once any fault occurs. But also we have to ensure that the protection doesn't work improperly for different scenarios. Speed and selectivity are also taken into account for the different setting criteria. And for sure, the maximum protection at the lowest cost will be always one of the main goals. For giving an illustration about this kind of scenarios, I am showing here a power system example. And in this power system example, what we have here, they are 4 generators, and we have 4 fault locations. This slide means, for example, that fault number 1, we are getting here that for this fault, what would happen if the breakers that did the operation were number 1, 2, and 4. That means that if this fault occurs, Breaker number 3 and 4 should be the primary protections. And if we are having here that the breakers that tripped were 1 and 2, we can see that the number 3 didn't work properly as primary protection, but number 1 and number 2 worked as backup protections. Likewise, we have here the fault number 2. In this fault, we are having the operation of breakers 3, 5, and 8. 3, 5, and 8. That means that the primary protection, that is number 6, that didn't work. But the backup protections worked properly. The number 3 has the operation of breaker number 10, which means that the primary protection worked properly, since everything is okay. Finally, for the fault number 4, that means the operation of number 11 and 8. So in this scenario, we are having an strange behavior because the 11 is the primary protection. So that should be the only one that should operate. But we got the operation of number 8 that initially number 8 has directionality, and in that case, it should not detect faults in this way. And for sure, this breaker doesn't have any relation with that fault. These kind of challenges are very common in the protection schemes coordination. And for that, typically we used power system analysis tool that will allow to set properly the selectivity of the network. For doing that, let me present here some concepts about the setting criteria. And the setting criteria is based in some protection coordination principles. The first one is the selection, the proper selection, in order to assure the relays in the relays operation in a reliable and selectivity way. The other case is the proper coverage of the thermal limits that is more related to the magnitude of the current, that in general we have to consider the thermal limits in order to send tripping orders for the disconnection of the fault once any fault can cause the thermal violations of the elements like the transformer, like the transmission and distribution lines, like the generators, like the machines, and for sure, like the users. Finally, proper settings of instantaneous and time delayed units. And that opens the opportunity to implement selective coordinations that they are mainly composed by two types of protection schemes that I will illustrate later, that are mainly for overcurrent protections and for distance protections. The other kind of protections are known as unit protections, since when they detect the pickup, they send instantaneous order, typically in order to disconnect the system. Well, we have here some standards that are highly used for the protection of the transformer and synchronous generators. These standards are used yet, since we find this kind of power elements in the electrical networks, and surely we will continue finding them. However, these standards are based in conventional theory of the short circuit, that they come typically from synchronous machines or from turbo machines, and this behavior was considered for these standards. But today we are not only speaking about synchronous generator. Today, we are also speaking about the inverter-based resources they have another kind of behavior. Since we can see that we have high currents once any event occurs, we have here that the current doesn't increase a lot in these kind of systems. This slide is showing that for these kind of generation systems, we have minimum required protections functionalities. For example, the generators, the synchronous generators, they have to be supported by out of the step relays, by loss of excitation relays, but we can see that they are not required in this kind of protection. In this side, we have that for the inverter-based resources, we have some protections like the directional power relays, like the overcurrent protections, like the overvoltage, like the frequency relays, like the undervoltage relays, among other functionalities that we are able to implement as the minimal requirements on these protection systems. Well, to talk about the overcurrent protection, that is one of the systems that I mentioned before about the selective coordinations. The overcurrent protection is one of the most typical applications in the protection devices. Why? Because they have different characteristics that we can coordinate. Some of them are based in specific current levels. Some of them are defined in specific time delays, inverse characteristics, or hybrids between them. I am presenting here some typical criteria for pickup setting of this kind of protections. Some of them are for distribution lines, some of them for protections between substations and for transformer units. It is notable how here we have, for example, that depending on the fault location, we can set the overcurrent relays. And if we can see that if we find proper settings, we will be able to provide some time delays between protections as primary and backup protections. Some standard means, for example, typically this time delay, the difference between the time is recommended to get about 200 or maximum 400 milliseconds between the operation of them. And get this kind of intervals of the time is one of the challenges for the coordination of the protections in the electrical systems. Another selective protection is about the distance protections. And I am showing here some examples or some criteria according to the standard for the generator protection. And this protection is different about the overcurrent protection because this protection is based on the impedance graphic. And depending on the behavior of the load and depending on the behavior of the fault once we have any event, the relay is able to send a trip signal depending on the operation zone. I mean, if we have zone 1, zone 2, or zone 3, and it depends about what is the position of, what is the fault location on the system. Well, let's talk about the modern protection schemes, because as I said before, we are having here a new transformation of the networks. Since before they are mainly power systems, now we are speaking about the smart grids. And the smart grids has many characteristics as I presented before. And in that case, we are having some challenges. And how can we improve the operation of the system, taking into account the different challenges that we have? And I'm going to start here presenting some recent publications. For example, this publication is from the IEEE committee that is presenting here the protection challenges and some methodologies for the protection of the transmission systems with high penetrations of inverter-based resources. And we can see how these kind of publications have the recommendation of the direct transfer trip or permissive overreaching transfer trip schemes or directional comparison blocking. Some of them are based in communications because when we have the opportunity to communicate the relays, some of them can block the operation of any other remote relay. Another publications that we have is the impact of the inverter-based generation for the bulk power system, and that is mainly related to the short circuit contributions because maybe you remember the waveform of the current that I presented before, but we have different challenges because the impact of these kind of systems. And they cause, for example, different responses on the relays, misoperation because the improper direction of the negative sequence of the elements due to the high penetration of these kind of systems, the lower systems inertia, the frequency issues, the short circuit levels. You can see that in this kind of systems, the short circuit level decreased in comparison with the short circuit levels with synchronous machines. And the standards for the short circuit calculations, for sure, as I presented before, they were based mainly in synchronous and turbo machines generation. Well, other modern protection systems, and this is not a protection system specifically, but the fault location, isolation, and service restoration is one of the advanced applications that we find in the smart grids. Because the fault location, isolation, and service restoration that is known as FLISR allows to implement some proper strategies in order to reduce the time where the energy is not being supplied, in order to increase the reliability by opening and closing the corresponding breakers on the distribution networks in order to extend the operation of the system. To understanding that in a better way, I have here an illustration of the FLISR application. We have here three substations, and maybe we can consider the substations as the connection to the transmission system or new generation or new generators on the distribution system that represent different sources. But it is very, very interesting that, for example, in this illustration, this breaker and this breaker, they are open, and that means that we have three feeders. Feeder in blue, feeder in yellow, and feeder in red. In this case, what would happen if any fault occurred? If we have the fault in this location, this breaker will open due to the high current that we have because of the fault. And this breaker and this breaker were initially open. FLISR application means that we can close the other breakers and open the corresponding part of the network just that has the fault. And in that case, we are increasing the reliability since we are able to supply the load for the healthy part of the network. Well, another applications that we find in the modern protection schemes is the adaptive protections. The adaptive protection is due the opportunity that we have by the change of the setting group in the protection relays, depending on the topology, depending on the loading or generation levels. And we can see how different application in the state of the art of the protection can provide the new setting of that the protection should have depending on the topology of the system. To illustrate that, we have here, for example, this more or less, this is a conventional system. So we have here a substation that we have here a distribution for different loads, two transformers in parallel, and one generator here, and the grid, the external grid connection. If we are speaking about the coordination between the relays, let's talk about what would happen if we have a fault in the secondary side of the transformers. The breaker number one, or the relay number one, will have the own inverse time characteristic. That means that if we have a short circuit detected by this relay will detect a fault, and that fault level will have the corresponding time. And we can see that this current comes from the current that comes from through the transformer. And if we are speaking about the current that the relay number 2 can measure, we can see that that current will be more or less the 50% of the total current that the relay 1 were measuring. In that case, for that short circuit level, we have to ensure a time dial that for that level in the relay number 2, we can get the proper setting, and that time dial could be, for example, 200 or 400 milliseconds. For here, we are finding here some criteria on the coordination principles for the selectivity for this scenario. However, what will happen if we open the other transformer? If we open the transformer T2, what we are getting is a change of the topology, and that change will impact the short circuit level. Why? Because in this case, we will get a new fault current, and that fault current will be the same between the relay 1 and the relay 2. Everything comes here. But also relay number 1 will see that the current is reduced, but the number 2 will see that the current has increased. Based on that, the new setting for that new time should be for the operation of the relay number 2 that will ensure the time dial that will provide the new setting of the relay. We can see that in one state, we have the setting of the relay number 2 in this part, but for the other state, the relay setting has changed. Well, and what happened with the distributed generation? Because that is something the same. Because if we have a new generator in this part, we are having that in normal conditions, the fault current will consider the current from the generator plus the current from transformer 1 and T2. But if we don't have the generator, the current reduced. The current is reduced. Why? Because in this case, this short circuit contribution is not considered. Let's present some examples about this kind of different applications using the modeling and the protection assessment with NEPLAN software. What I have here is my NEPLAN application, and I have here, for example, an initial scenario of this very, very simple example. This is a very, very simple example that will allow me to illustrate how does NEPLAN help on the implementation of automatic settings calculation depending on the topology. Why? We are having here that for this fault, the tripping time of this relay is around 246 milliseconds. And even this operation is faster than this relay that is having 244 milliseconds. We are not having proper coordination here because we have to consider that for this fault location, the operation as primary protection should come from this relay instead of this one. How can we improve that? Let's open here the NEPLAN characteristic of the overcurrent relay. And in this case, let's see, for example, what is the current setting that we have. NEPLAN allows to get directly in the window of the relay that for that short circuit level, we are having the operation out of the scope of the instantaneous unit. Can we change that manually? Yeah, we can modify the setting of the protection in order to move according to the possibilities of the system. But let's allow NEPLAN to determine the best tripping, the best backup, the best pickup setting of the protection. How can we set that? We will set that for example, three-phase fault, We can set a short circuit level here in this node, node number 3, and let's run the simulation for that node location. We can see that we are having the impact for having the short circuit level in that. That means that if we have the short circuit in this location, the current is around 1.4 kiloamps. We can use that short circuit level. And what we can see here is the short circuit level comes here, and we can set some criteria. For example, what happens if we set the instantaneous unit in the 50% of the short circuit level? We can change the setting of the protection. And if we come for the new operation, we can see that we have moved the pickup of the instantaneous unit. If we run the simulation now, we can see that for this fault location, the tripping time of this relay is now working in the instantaneous unit. And for sure, we are having here a very, very convenient difference on the time between both relays. Well, as I am mentioning, this is a very, very simple example, but it has allowed me to present some characteristic for automatic CPLAN setting with NEPLAN. However, NEPLAN has the possibility to use any kind of simulation of any kind of application using web services. And it allows to implement customized solutions. We have, for example, this internal application that we developed in our team, and here I can access to our server. This is an application that we implemented using the NEPLAN web services. Remember, the NEPLAN web services are highly convenient since anything of the application can be accessed from any external application. That means that, for example, if we are going to get this project name is, for example, automatic setting number P2, and we use the scenario auto setting, we can get that project. And in that applications, we are getting the different elements that we have in the project, and we can set for what elements we can get results and automate different fault locations and different resistance failures on the system. That means that we can, using everything with NEPLAN web services, I can provide automations, and we can see that just for this small sample, we have to run more than 100 simulations. So can you imagine how many simulations do we need in more complex networks? In distribution networks with a lot of nodes in the distribution networks and in the transmission networks, the number of required simulations is too high. So I will continue doing the illustration of the different applications with NEPLAN while this number of simulations finishes. So the other example that I have here is this system. So this system is related to the example that I showed initially with the transformers in parallel. Since if I work the short circuit simulation in this point, we can see that when we have everything connected, we are having a selective coordination between this relay and this relay, because for this fault location, this relay is tripping first, and the difference between this relay and this relay is higher than 200 milliseconds and lower than 400 milliseconds. So everything is here, is good in this scenario. But what happens if we have another state where this transformer is open? Or what happens if we open this switch? So we are changing the operation, we are changing the topology. And if we run the simulation, we can see that the tripping time has changed, And in that case, we are having selective, yeah, we are having selectivity since this protection trees first, but the delay between both operations is not bigger than 200 milliseconds that initially it was our criteria for this example. That means that we have affected the time delay for the coordination of this system. So NEPLAN allows to validate that, and in different complex networks. For example, what would happen if instead we have or not the distributed generation, and we can validate for all the combinations of the system if everything is working good or not. How can we do that? Initially, we can validate the protection assessment directly on the relay mask because for specific port locations, we can set here the assessment of the setting for this state, but also we can use the protection assessment of NEPLAN. The protection assessment allows to implement the automation of the different possibilities in the fault locations, maybe in nodes, faulted nodes, or maybe faults on the lines that will give us some indications. For example, what would happen if for three-phase faults working in the initial state where this switch is closed, and we will validate the selectivity with a minimum time of 200 milliseconds. If we implement the protection assessment, we can see some results. Let me present here what would happen if everything can work good, and what would happen in this kind of scenarios where the software shows yellow or red message. Because this case, for example, means that if we have a fault in this node, the operation between both relays, because we can see that this relay and this relay have the same setting, so they will have the same time. So this example is showing the difference between both protection is not bigger than 200 milliseconds, but the reason is clear. The reason is clear because we don't have any protection here. That means that if we have a fault in this location, we have to clear the fault in the protection that we have to add here in the primary side of the transformer. So this is the same in this case. In this case means that, and this is a red color, because that red color means that if we have a fault in one of these locations, therefore the short circuit won't be cleared. And that means that we have to install protections here. So this is more related because we don't have protections in this part. However, let me now present what will happen if we make the protection assessment when the state changed. Remember, the state one means the opening of this transformer. So if we make the protection assessment for this new state, we can see that we have the same issues due to because we don't have protections here, but we also have here this part of the network. And this part of the network is exactly the improper coordination between this relay 88 and this relay A2. Why? Remember, we said minimum coordination time of 200 milliseconds that now is around is around the difference between these tripping times that we are getting here. So protection assessment of NEPLAN allowed to get the validation of the existing settings of the network, but also it allowed to check using the automatic setting of NEPLAN if we can change that automatically or not. For sure, we can change that because for this operation, NEPLAN allows to define a new setting group. For example, I can change the setting group of this relay because once I work the simulation, we can see that we have increased the tripping time here because we moved the setting, And now the difference between both protections is bigger than 200 milliseconds and doesn't exceed the 400 milliseconds. So this is the example for the setting criteria. And for sure, the same impact if we can connect or disconnect the distributed generator. So NEPLAN allows to get the different signals for the different topologies. So write to my email. I will give you my email if you would like to see what is the solution once we change the topology when we connect the distributed generator in order to give the proper selectivity for the whole system. Well, finally, I have here a complete selectivity scheme. And this selectivity scheme considers, for example, how can we create selectivity diagrams for a specific part of the network that will consider the different elements. For example, I create an automatic selectivity diagram considering the machine and the circuit breaker. So NEPLAN offers many tools for the coordination of the protections graphically. So that means that, for example, we have the starting curve of the motor and we have the tripping time of the protection. So we can see that, for example, what will happen in the scenario that the protection is not defined properly. In this scenario, this breaker will open the machine just if we are going to start the machine. So that is an improper setting of the protection. So graphically, NEPLAN allows to get the proper setting using the selectivity diagram. So this example has many coordination principles. We have here the coordination of the machine. We have here the coordination of the motor or in this case, they have just 50 horsepower. So the coordination using the thermal limits of the cables. So the coordinations for protections in the grounding systems, coordination between the breakers and the relay, and NEPLAN allows to see in the diagram which element correspond to that. And for sure, we also consider here the thermal limit of the cables, and many examples using the proper coordinations of NEPLAN graphically. For example, if we select this protection and this protection, NEPLAN allows to provide the difference maybe in time between both protections, or maybe in current between both protections. So this selectivity diagram is highly used for the coordination of the protections graphically. And for sure, we can see that the user interface should be very user friendly in order to provide the proper selectivities in different parts of the system. So we can select a specific element and create the specific report that NEPLAN will provide automatically using what are the final settings. And those settings would be according to the selectivity scheme that we implemented. But also we can export the selectivity diagrams in different formats, maybe as PDF, maybe as a picture, Word, or Excel files. Well, so these are the examples that I have here with NEPLAN. So before continue with the application, I can show it here that all the simulations that we did here, we have completed here 128 simulations automatically. So we can create our own report. And this is a customized solution. And this customized solution is just for giving an illustration about all the possibilities that we have when we can automate any simulation using the NEPLAN web services. Well, however, the NEPLAN web services have many advantages. For example, the protection device management systems implementation, because in this architecture, we can see how in real time we can import and export the relay settings. We can validate them on the network model. We can give permissions, level access for the users, and validate the relay setting calculation and check if for specific topologies they are working or not. So the architecture using NEPLAN web services allows to implement customized solutions for any kind of customer. And we can see how using communication protocols like IEC 61850 or FTP, we can send through to the application servers, maybe an SCADA server, maybe a server for the protection assessments, or maybe a server for the protection management systems. We can connect the NEPLAN web services to any application in this server. And for sure, one of them could be for getting automatic settings or could be for the protection assessment in order to validate the existing settings on the network. The another part that I presented here was the protection assessment. Since we can see that many possibilities on the topology states, on the fault scenarios, and the loading states, many possibilities, even the short circuits on the line, they are automated, and NEPLAN will give an indicator about where the protection selectivity fails or not. Well, so I have here the final conclusions of this webinar. First of all, power systems, now we know that we are having a new generation of power system, because now we are speaking about the smart grids, and they are changing the operation, the conditions of operations, but also we can see that they can improve the reliability and the efficiency of the network. So smart grids are providing reconfigurations of the feeders, but also connection of the renewable sources that has affected the conventional protection schemes, the conventional setting criteria in the electrical networks. Also, we have here that today we have different manufacturers that are providing different setting groups, and the setting groups can be easily implemented in adaptive protections. And the adaptive protections, for sure, as I presented, can provide the required solutions for the selectivity. It doesn't matter the topology, since automatically the protection will change the setting. I also speak about the FLASAR. The FLASAR is essential to increase reliability in distribution system, but it must consider the relay settings. Finally, the overall process of relay setting, considering several groups, demands a comprehensive calculation process, which we can see that NEPLAN can support this kind of scenarios. NEPLAN can support the integrations of real time for the operations of the smart grids in proper coordination protection schemes. So I present here some references that I used for this presentation. I invite to all the attendees to review the state of the art in the protection schemes for the conventional network. And now we can see that we have different challenges due to the implementation of smart grids. I invite you to follow us in our QR code. You will be directed to the NEPLAN contact form. So we are NEPLAN representative in the Americas, and our services using NEPLAN includes training in protection schemes and smart grids using real technologies. We have here a picture of our laboratory that has a real microgrid implementation using different IEDs. And also we have integrated that into our SCADA system, and the SCADA system was automated using the NEPLAN web services. We can design, control, and protection schemes. We can test any IED or SCADA system, and for sure we can implement the proper setting criteria for the protections. NEPLAN can be easily integrated to any external system using the web services, like the GIS systems, like the SCADA system, like the smart grid applications, some of them I presented in this webinar, protection device management system, and the asset management systems. Since NEPLAN provides the own asset management model. Well, so thank you very much, Gabriela. I don't know if we have some questions from our attendees. So
Thank
this
you.
is my, yeah,
Sorry.
thank you, Gabriela.
Yes, thank you very much for your information, for your informative presentation.
Perfect. This is my email. If any attendee would like to contact me, if you would like to get more information about the application that I presented here, and for sure, if you would like to get information about NIPLAN and our trainings.
Okay, great. If anybody has any last minute Q&As, please submit them now and we will do our best to answer them. It does appear we have some questions here. The first one says, if we can simulate DDT goose or other communication messages.
Well, I understand for this question, the GOOS applications, I understand that is related to the IEEE, so sorry, to the IEC 61A15. And this standard allow communicate mainly for the substations application, the GOOS message. So the protection schemes using the standard IEC 61A50 are opening a new generation of the system, since we have in real time the samples of the signal and the proper state using GOOS message. However, we have to be careful when we use GOOS message, because the communication in the substation using GOOS and sample values with the IEC standard is more related to the operation inside the substation. The IEC 61A50 standard also have a standard that is related to the communication between substations, that is more related to the MMS application instead of GOOS. But that means that maybe if the architecture of the communication system is proper to send GOOS message, that scheme could work. In the other way, we could work with another kind of standards that will send the state of the tripping relays. But yeah, the GOOS applications are now studied and implemented in this kind of systems, and even the real-time technologies like hardware in the loop are allowing to validate the POTTs and the DDTs using the standard of IEC 61A50.
Okay, great. We have another question here that says, what did you simulate with your own tool via web services and NEPLAN?
Well, the tool that we implemented is mainly oriented for the automation of the different possibilities. I used here a small system, but what we can see here is we have a power system, and the power system has many possibilities in the fault locations and the different resistance failures that we have in the network. So we implemented a customized solution that is able to automate all the possibilities. In the small system was 128. And for each simulation, we are getting the short circuit levels. And for each short circuit level, we can validate the tripping time of the protection. So we have automated here different applications for that. But this is an external application just for illustrate the capabilities of the web services, because we know that, for example, NEPLAN allows to get the protection assessment that offers some visual indicators about the possibilities or the improper settings that we have in the network. But these applications has automated all the simulations. We have, for example, we selected these elements. So for each element, we will work with 3-phase fault, 1-phase fault, 2-phase fault, and for each fault, we have to see, yeah, what is the short circuit level, when we have a variation of the resistance failure.
Okay, great. We have another question here as well. Can we import the settings reports for the different brands of relays?
Import the settings. Well, so as I presented here in this slide, this slide shows a suggested architecture for getting the settings directly from the relays. The IEC standard 61A50 allows to send the settings using a MMS protocol that is more related to the state of the relay. The FTP standard file transfer protocol is typical also, and that is highly used to get the current condition of the relays. So since we have this kind of protocols to get the information from the relays, this information comes to the external server, maybe to the SCADA server, where is easily connected to NEPLAN using the web services. Remember, we can connect any functionality on NEPLAN to any external application like the SCADA using that layer of the web services. So this is the architecture that we suggest for the integration in real time about the current conditions of the relays.
Okay, great. We have one other question here. Can the NEPLAN protection assessment also be used in distance protection coordination?
Absolutely. Yeah, absolutely. In this webinar, I presented the example of the overcurrent protection, since that is one of the selective protection, but also the protection assessment work very, very good for distance protection. In that case, the coordination is done using the different zones, zone 1, 2, and 3, and the protection assessment will check if the tripping times, depending of the fault location, are according to the topology or not. But yeah, the protection assessment works very good also with the distance protections.
Okay, sounds good. That is all the questions we have today. So we'd like to thank you all for attending our webinar, and we also invite you to see our GERS Academy application to see this recording and the recordings of our past webinars. So to access our GERS Academy, you can go to gers.academy.gersusa.com, or you can email us at academy@gersusa.com. And this is a great resource to see our past webinars and this one as well.
Perfect. Thank you very much, Gabriela, and thank you very much again to all the attendees in this webinar. I hope you find this presentation useful. Have a great day.
Thank you, Leineker. Hope you all have a good day as well.
You too. Thank you.